Okay, so let's look at key exchange. And this will focus on how we get an encryption key from Bob to Alice. Okay, so here's Bob and here's Alice. Alice and Bob. So what we need to do is to be able to pass a secret key. We'll define that as a secret key. Only Bob and Alice will know the secret across, either from Bob to Alice or Alice to Bob, or for them to communicate openly and generate the same shared secret. This secret is used to generate the encryption key that they will use. Unfortunately, we have Eve in between. And Eve could be listening to all of their communications. So we need a way for this secret to go over to the other side without Eve discovering the secret. So we either find a way to wrap up this key and send it over and for Alice to be able to reveal it, or we can find a way to negotiate between Bob and Alice, even though Eve is listening, and to be able to end up with the same secret. From there, we generate our encryption key. Normally, it's an AES key. This is known as the Diffie-Hellman method that we'll look at. And this method here for encapsulating or protecting the key is normally known as public key transmission. Okay, so that's our challenge, is to be able to create that. Once it's created, we create what's called a tunnel, an encryption tunnel, and anything that goes into the tunnel is encrypted with the secret key. So as with symmetric key, then we just use the same key on either side to encrypt and decrypt. But even though Eve is listening to the communications, she shouldn't be able to break the tunnel because she doesn't know the secret key. And the secret key itself could be AES or ChaCha20, or really any type of method that we might want to use for symmetric key. Could be even RC4. But we can use it once for every session, or it could be a long-term key that we use. Just depends on our application. If we have something like a VPN, then it might stay alive for a while, maybe for a day or a week or a month. But normally when we're connecting for our secure communications, we use this key once, and then the next time we connect, then we'll use a different key. Okay, so let's look at the different methods that we have to allow Bob and Alice to be able to communicate. Before we do that, let's look at some key parameters involved in key exchange. The first one is what's called forward secrecy. Forward secrecy. And what's forward secrecy involves is that for every key that's generated, those keys will be protected in some way as they are communicated. So they are exchanged between Bob and Alice, and Eve has been possibly listening to all of the communications. Forward secrecy means that something is leaked, such as the private key of Alice. Then all of the keys from the past could then be revealed. So in this case, I'll draw the private key like this. This is the private key. and Alice also has a public key. So here is Alice's public key. And this is a secret key. Okay, so I'll draw that in green, I'll draw the public key in yellow, and then the private key, the key pair, like this. So with forward secrecy, Eve eventually has determined Alice's private key and then can reveal the keys that have been used in the past. If we can find the mechanism so that it doesn't matter if this is revealed, none of the keys will be actually revealed in the future. The other method, the other parameter that's important is ephemeral. And with ephemeral methods, then the problem with this is that when we're performing a key exchange, we use certain parameters, as we'll see. If those parameters do not change, then it could be possible to determine something about the encryption key that's being used. So any leak of a long-term key could actually reveal something about the keys that are being used. Okay, so those are two parameters that are important in terms of the usage of our keys. So now let's look at an extremely important method. And that method is known as the Diffie-Hellman method. And it caused quite a disruption within cybersecurity when it was created, and it also led to the creation of the public key method known as RSA. It was created by Whitfield Diffie and Marty Hellman, and they created the Diffie-Hellman method. And with this, in the core method, we use discrete logs. So if we have Bob and we have Alice here, what discrete logs gives us, if you remember in school, is that g to the power of x times g to the power of y is equal to g to the power of x, y. And g to the power of x to the power of y gives us this gives us g plus y, and this gives us gx. G to the x times g to the y gives us g to the x plus y. G to the power of x to the power of y gives us g to the power of xy. The great thing with discrete logs is that we now bring in a prime number, in that when we use the prime number, then our maths become still operational whenever we do a mod p operation. So that is equal to, say that, and we can operate in the same way with mod p's. If we take mod p's, then our maths still work. So the Diffie-Hellman makes use of this logarithm rule, and discrete logs brings in the mod of a prime number, mod of p. So let's look at the operation of it. We'll generate a random value of b for Bob and A for Alice. Then Bob and Alice agree on two values. A G, generator value, typically that's 2 or 3, and a prime number P, which is going to be large enough to keep the security. So then Bob will calculate G to the power of B mod P. And then Alice will calculate G to the power of A mod P. They then exchange these values, and then Bob takes A to the power of his value, B mod P, and then Alice will take Bob's value, raise it to the power of A, and take mod P. Hopefully, if everything works out, then they will end up with the same shared secret, K in this case. And the reason for this is that G to the power of A to the power of B is actually G to the power of A to the power of B. And over here we have G to the power of B to the power of A, and that gives us G to the power of AB, G to the power of AB again, and they should be the same. When we bring in the mod P, they'll also be the same on either side. So in this way, Bob and Alice can communicate openly between each other, and even though Eve is listening and she knows G and P, it shouldn't be possible because of the discrete log difficulty to determine the values of A and B. And only by knowing the values of A and B can you actually generate the same shared secret. Okay, if we take an example of this calculation. So if Bob uses a value of 7 and Alice uses a value of 9, then B, and we're using G of 5 and a P of 97, that's a prime number, then G to the power of B is 5 to the power of 7 mod 97, and I think that equals 40. Alice computes G 5 to the power of 9 mod 97, and I think that should equal 30. Bob sends over 40, Alice sends over 30. Bob takes 30 to the power of his value, 7 mod 97, and computes 51. Alice does the same, takes Bob's value, raises it to the power of 9 mod 97, and abracadabra, they end up with the same shared value there. Obviously the values that we use in real life are much larger because the prime numbers are much larger and the random numbers are larger, but that shows you how it actually works. In real life, though, we have another step. If we're generating an encryption key, then the step that we make is to use a key derivation function. So if we're negotiating our key with the Diffie-Hellman method on either side, we end up with a secret we then put it into what's called a HMAC key derivation function. On either side, same function. And if we want, we can add some salt into this. And that will create our secret key that we're going to use here. We have a key there. And that will generate a key of a given size, such as 256 bits or 128 bits or even 192 bits. And in this way, Bob and Alice can use the same key. Okay, so they negotiate with Diffie-Hellman method, they create the secret. The secret is then fed into our HMAC key derivation function using the same method on the other side, and that allows us to generate the key. This is a safe way of creating our encryption key. This generates the secret, and this will then generate the actual key that we were going to use. Okay, so that's using HKeyDF. And we can't just use any value of g to the power of x mod p, because some of the values don't actually work. And what we want is to be able to create a mapping from the value of x. We had all the x values here, and they should map to other values over here, and we should get a direct one-to-one mapping for all the values in here, having a unique mapping over here. And we don't want two values here to map to one value there. So the values we'll have here are between 0 and p minus 1, and the values here are 0 and p minus 1. This is the values of x mapping to the key or the value that we get here. So we need to pick g in order for this to actually work. So if we pick a generator value of 2, and we'll try a value of 3, and we try different values of x for say 2, 3, 4, 5, 6, 7, 8, 9, 10, and we'll use a prime number of 11. Then if we go through the values, 2 to the power of 2 mod 11 is 4, of course, 8, 5, 10, 9, 7, 3, 6, 1. So that's all good, because we can see each value of x relates to a different value when we do g to the power of x mod p. But watch when we use a g value of 3. In this case, we end up with 9, because 9 to the power of 2 is 9 mod 11. Then we get 5, 4, 1, 3, 9, 5, 4, 1. Missed one out there. 4, 3 should be the 5, 7 should be the 9, and for the 6 we get 3, 1, 4. I've missed one out there, but the main point here is that we can see that the values are repeating within all of the values of x. So g equal to 3 would not be possible. And it's quite a simple little computation to be able to determine for a given prime number whether our generator value, this is called the generator value, is acceptable with this prime number. And in the lecture I've shown what that actually program looks like. Okay, so this is our calculation of this G generator, and when we're doing this in real life, we randomly pick a prime number, and then we do a quick check to see if the generator value is acceptable for that prime number. If not, we'll go and pick another prime number. Okay, one program that we use to be able to generate the value of G and P is OpenSSL. With OpenSSL, we can run the dhparam command. We can define out and then give our key name. This is where the output will go to for G and P, and then we can define the number of bits that we have, and also define if we have a text output. The file that we create then, 1.pem, then shows the prime number that we're using and also the generator value, G. Typically this is 2 or 5, and when we're generating the values we can define another parameter to define. If we say -5, it will use a generator value of 5, but the prime number will be defined something like this in hexadecimal, and overall it will have 768 bits in there. So this is the way that we generate a random prime number, and also we actually define our generator value. And as we see here, we need to, the OpenSSL needs to check that the generator value is one that can be used with the prime number that we've actually created. There are 3 groups that we can use. Oh, sorry, there are quite a few groups. The base group is called group 1, and that's a 768-bit prime. This shouldn't be used because it's at the limits of being able to crack Diffie-Hellman key exchange. Then we have group 2, which is 1024-bit prime. Group 5 is 1536 bits, and we can get larger ones than that, but we normally start about here for over 1500 bytes for our Diffie-Hellman, because these two are fairly weak in their security. And it was found out that a paper was published known as imperfect forward secrecy, where it was possible to actually determine that certain web sites were using default parameters for G and P. The weakness of the Diffie-Hellman method, though, is Eve in the middle. And with Eve in the middle, so we have Bob and Alice. But unfortunately, we have Eve right in the middle of the communications. She sets up a proxy or something like that. And now what happens is that Bob communicates with Eve and Eve communicates with Alice. Bob thinks he's communicating with Eve directly, but he's actually going through Alice directly, but he's actually going through Eve. So what can happen, obviously, is that Bob can send his G to the power of B value, and Eve will generate E. So the key that he will generate will be this, and the key that will be generated over here will be this, assuming that Alice takes A, Bob takes B. So we can see that we now have 2 tunnels between here and here. Basically, we would encrypt with G to the power of B for this tunnel. Eve would decrypt it and then re-encrypt with this key. So this is the main weakness of the Diffie-Hellman method, and we would probably never use this in real life, what we often do is to be able to make sure that Bob can actually know that he's communicating directly with Alice, and we would do that with normal public key encryption methods. Okay, so let's now look at a very important area, and it's the method that's most often used for our key exchange. Unfortunately, the key sizes are becoming bigger, so the method that we typically use now is elliptic curve Diffie-Hellman, and this allows us for much shorter keys, much shorter prime numbers, and so on. Just to recap on elliptic curve, so this is what the elliptic curve looks like in its analog form. It's not the discrete form, but we'll just assume that it looks a little bit like this. With elliptic curve, we pick a base point. I'll draw it big G rather than little g over here for the discrete logs. This is a point on the elliptic curve. We then work out a private key, so let's call it SK, which is a scalar value of 256 bits. We then add this point this number of times to get the public key, and we'll call that PK. Okay, so our public key is a point on the elliptic curve, and we just use point addition to be able to find that. Our private key is here and our public key is there, and it's too difficult for Eve to be able to determine this secret key, even though she knows G and the public key point. The main parameters that we have for this are, this is our elliptic curve equation that we have. So an elliptic curve is defined with A, B, P, G, and also the order O in this case. A and B are the parameters. If you're interested, for Bitcoin, A is 0 and B is 7 for the Bitcoin curve. P is the prime number, G is the base point, and O is the order. Basically the number of points that we have on the curve. Okay, so that provides us with our basics of our key. And with this we can use OpenSSL to be able to generate these, or to be able to define these values. So the way that it works is that we have Bob and we have Alice, and again they generate their secrets from there. They agree a base point, a prime number, and all these values here. So Bob generates B, G, which is G added B times, and Alice generates A, G. It's not too difficult to determine the values of A, even though we have B and G there. We have big A and G. So Bob sends his value over, Alice sends her value over, and the shared key is equal to Bob's secret times A. Again over here, A times B, and that becomes B A G and A B G. And because of the wonder of these operations, these are the same values that we have, and we have the same shared key. Obviously we then go and probably use the HMAC key derivation function to generate the actual key that we want to use. Okay, so this is elliptic curve Diffie-Hellman, and it's a very fast method. It's using public key encryption as we would normally have it, and it's exchanging the values from there. If you're interested, it's used in the Tor network. So in the Tor network we have onion routing. So we have some nodes, and then we have Alice over here which might be a remote website. There's Bob, and we have intermediate nodes that are just little routers. With this method, what we do is that we find a route for our traffic, and this one is called a gateway node or an exit node, and this one is the entry node to the network. We use elliptic curve Diffie-Hellman for each of the nodes to communicate a key with Bob. So in this case, the first key we'll define as red. So we use elliptic curve Diffie-Hellman, and then the next key is green. Okay, so negotiate another key, and then the last one we'll make purple. Okay, so we'll negotiate with Bob. So Bob has these three keys. So what happens is that we take our data. So here is our data. We then wrap the data with the purple key. Appreciate it's a bit difficult, make that purple. We wrap it with the purple key. And then we'll wrap it with the green key. And then finally, we'll wrap it with the red key, this one here. So this is the data here. So when it hits the first node, the first encryption key is taken off. So we end up with the green and the purple. When it hits the next node, the green encryption is taken off. And when it hits the final node, we only have the purple key here. And this gateway node will then decrypt that key. And then we'll have our data at the end. So this is known as Tor or onion routing. And none of the nodes can actually reveal the data apart from this gateway or exit node. We wouldn't be able to see any of the traffic here because we don't have the keys here. But each node negotiates the keys that they want to use, and they will reveal their keys when the data is sent through them. So none of the nodes can actually reveal any of the traffic. When it comes to popular curves that we have, so curve 25519 is a popular curve method that we can use. If you're interested, it uses a prime number of 2 to the power of 255, 1 minus 19. That's where it gets its name from. But in Ethereum and Bitcoin, we use SEPT256K1. That has this parameter here, and it uses a 256-bit prime number, as this does too. The key exchange method, elliptic curve, Diffie-Hellman. The method we use here is often known as 25519 key exchange using curve 25519. Other curves include curve 256, and if we want an even bigger curve, we can have a 521-bit prime number to make it even more secure to give us this. If curve 5519 isn't strong enough, then we can actually use curve 448, which is an extremely large 448-bit prime number compared to that one. So that gives us more security, but those are the typical method, and we define this as X448 as a technique that we can actually use there. Okay, so this is the key exchange method. Another way of exchanging the keys is using public key encryption. And in this method, we encapsulate the key. Okay, so let's bring back Bob and Alice here. Okay, so let's see what our keys are. So Alice has a public key here, and she also has a private key. And I'll draw the private key like this. And for the symmetric key, I'll draw it like this. Okay, so this is the symmetric key or the secret key. This is the private key of Alice, and this is the public key of Alice. Okay, secret key, symmetric key, public private key, these are a pair that go together. If I encrypt with one, I decrypt with the other one. So Bob wants to get this key over to Alice using a public key encryption. So for this, what we do is that Alice sends over her public key to Bob. So that Alice might be a website. The website will return back a digital certificate with the public key actually on it. Now Bob will take his key and then encrypt it with Alice's public key. Let's send that over, and the only key that can now decrypt that is, guess what? The private key of Alice. So when this is received, we apply the private key, and hopefully what will be revealed is the secret key. They can then create the tunnel between themselves using this shared key. The problem with this method is that a long-term hack or a hack of Alice's private key can actually reveal all of the keys that have been used. So TLS 1.3 doesn't use this method anymore. It will use this type of method with the elliptic curve Diffie-Hellman and to do the key exchange that way. Okay, so that's provided an overview of key exchange methods. Just as a last thing, there is what's called a key distribution center. And these are all moving towards host-to-host generation of the keys. Sometimes, such as when you have IoT devices, you might actually want to create a key distribution center. And with this, Bob and Alice want to use an encryption key and don't want to negotiate or aren't allowed to negotiate a key. For this, we can use a key distribution center to be able to generate the key that both Bob and Alice can actually use for their communication. There are many ways to do this, but really we centralize the keys that we're using into the key distribution center. And so that Bob and Alice don't need to communicate with each other as they did here. They can generate the keys from the key distribution center. Okay, so that's covered our main topics that we were looking at. We looked at the main methods, the issues that we have, the Diffie-Hellman method, how we can generate the values of G and P from here, and then how we generate the key. We then looked at Eve in the middle for Diffie-Hellman, the elliptic curve Diffie-Hellman method, some Tor routing, onion routing, different methods that we have, then how we can use public key encryption to be able to do this, and then finally we have key distribution centers. One thing I must say is that post-quantum crypto is coming along, and it will replace the methods such as public key encryption and elliptic curve, because these methods can actually be cracked with quantum computers. So we'll see a whole lot of new methods used for key exchange mechanisms being standardized in the next few years. Okay, thank you.